Hello, my name is Devyang, and this will be a presentation on my Lab 5 for E104 Task 2, the COVID-19 modeling. And I just shared my screen, as you can see. So, what is the Siddharth set of differential equations? The Siddharth set of differential equations is a set of differential equations that helps us model a pandemic in terms of the recognized, the threatened, how long it will spread, how quickly it will spread. Those parameters are listed here, the susceptible, the infected. It's basically in order to predict how a pandemic will behave over time. In our case, we've chosen days, but this can be done for years or weeks. And our population is going to be in terms of 0.2, 0.4, 0.6, 0.8. So that population represents the people. So moving on to the code. So we have our initial time, which is T0 is equal to 0. TF is equal to 1. So that's from here, from 0 to 1. And the step size is 0.01. So that's the step size in between 0.0, 0.2, 0.4, 0.6. And the parameters are the variables that we get used for modeling the differential equation. So in this case, we have alpha, beta, gamma, delta, epsilon, etc. These variables represent a set of they represent the differential equation variables, and that is basically a those are the parameters that we used for modeling the differential equation. So each one of those variables, they represent different parameters, such as the COVID-19 spread rate, the rates for infection, susceptibility, etc. And they continue all the way to sigma, alpha to sigma. And these are the differential equations that we've chosen. Uh, but it's shown for all the variables, even though we're only going to be plotting the susceptible, infected, recognized, and threatened. We have to, for the code purpose, we have to display all the equations because they all relate to each other. So def.s, SIDART, this is basically saying alpha times I plus beta D plus delta R. That is shown right here. That's the Siddharth's dynamical system consisting of 8 ordinary differential equations. So this represents each stage over a period of time. That's what we're trying to plot uh, in Python. And each of these values, the beta, alpha, they all get inputted into the equation and it spits out a variable. So that's what we're trying to model. And this is the Moore machine or the Mealy machine that's represented. The finite state. It's one of the finite state machines. We've got susceptible, we've got infected, diagnosed, healed, ailing, recognized, threatened, and extinct. So this represents our basic model. But we're only going to be plotting 2 of these states as stated in the directions here. Model states S and I, and we have 2 states from our choice, so we're going to have a total of 4. So again, when we go back to the code, these are the sets of differential equations that we modeled. And this represents basically all of this. That's the Siddharth set of differential equations that we just shown you, but right here. So 1 through 8. So once we have that established, we set up our population size, which in this case is going to be around, we have around 60 million. So each of these variables, they represent the variables that are going into this function. So these functions, we'll call them. So we have I, D, A, R, T, H, E, S. So I represents infected, D is diagnosed, so the people who are diagnosed with the disease, ailing, the ones who are like continuously sick with it, recognized, those are um, the recognized set of populations that have been recognized with the disease. Healed is the people who've recovered, extinct is death. Susceptible represents the susceptible group of people that are likely to contract the disease. And we have our number of steps, which is int tf minus t0 over step. And we have t in range 1, number of steps plus 1, preview t minus 1. So this updates all the variables. So we're appending it. So we're appending basically these variables. And this will all go back to this function call right here. And now we're going to shift to the plot. So I've adjusted the plot such that it only plots the S, R, I, and T. So those are the 4 parameters that I chose to plot in the Siddharth differential equation model. So plt.plots SB minus label susceptible line width 0.5. So this basically sets the label susceptible. So in the plot, as you can see, susceptible is represented by the blue line right here. And then line width is 0.5. So that's the thickness of the line. So PLT plot I G minus label infected line width 0.5. So that's again the line width 0.5. That's representing the thickness. And now we are looking at the infected. So that's the green line right here. And that's spread out over 100 days. And then we have PLT plot R M minus label recognized line width 0.5. And then R M minus label recognized. So the recognized line is right here. That's the red line, or rather the pink line. And it gets plotted right here. So that's also spread out over from 0 to 100 days. That's our time span. And then we have basically we have threatened. So that's the last set. That's the last date that I decide to plot the threatened. So we have PLT plot T Y minus label threatened. So SIRT that gets called from here. So these are the appended variables that we're using to plot the Siddharth model in Python. So plt.plot T label threatened line width 0.5. So that's right here. Threatened is the yellow line, as you can see here. So that represents the threatened line. And then plt dot label x label time days. So that's right here. That's going to be our x-axis in this case. And then plt dot y label population people. So that's going to be our x-axis. So it's basically x-axis is going to be our population, or the y-axis is going to be our population. The x-axis is going to be our time. So that's the parameters that we've chosen to fit our Siddharth differential equation model. And then plt.legend, upper right. So this is basically setting up the legend for the graph so we can know which parameter is which line. And then plt.gcf set.dpi, that just sets up the resolution of the graph, the resolution of the legend. And then plt.show, that's basically a built-in Python function call that just displays the plot. So this has been the E104 Lab 5 Task 2, the Siddharth differential equation modeling. Thank you so much.